In this lesson, we're going to be graphing quadratic functions of the form f of x equals ax squared plus c and solving real-life problems involving functions of the form f of x equals ax squared plus c. Graphing f of x equals ax squared plus c. When c is greater than 0, the graph of f of x equals ax squared plus c is a vertical translation c units up of the graph f of x equals ax squared. When c is less than 0, the graph of f of x equals ax squared plus c is a vertical translation, the absolute value of c units down of the graph of f of x equals ax squared. The vertex of the graph of f of x equals ax squared plus c is 0, c, and the axis of symmetry is x equals 0. So all we're doing to our f of x equals ax squared from our last section that we looked at is adding this c term, this constant. And we know that whenever I add something outside of the function, it's going to be a vertical change, and since I'm adding it, it's going to be a vertical translation. So all this plus c is going to do is either translate my parabola up c units, or if c is negative, then down the absolute value of c units. For this example, we're going to graph g of x equals x squared minus 2 and then compare to the graph of f of x equals x squared, the parent function. So whenever we're graphing, we should make a table of values. So I'm going to have my table here, x and y. And remember, I always want my vertex in the middle of my table. So I'm going to make my values at least 5 and more if I can fit more. So know that since all I'm doing is vertically translating my graph, the x value of my vertex is still going to be 0. And if I plug 0 in, 0 squared is 0, minus 2, that's negative 2. Okay? And you can just look at whatever this c term is. If there's no b term, which there is no b term here, then the c term will be the y value of your vertex. Okay, so this is where I'm going to start here. Then I'm going to surround my vertex with points. So I'll do 1 and 2, and then negative 1 and negative 2. And remember, the vertex also contains the information of the axis of symmetry. So whatever the y value is here is going to be the same thing here, and then whatever the y value is here is going to be the same thing here, and so on. Okay, so I'm just going to plug in some values. Well, 1 squared is 1, minus 2 is negative 1. 2 squared is 4, minus 2 is 2. And let's see if I can fit one more on here. So if I do 3, well, 3 squared is 9, and then minus 2, that's 7. So that's not going to fit. So anyway, I can rewrite this number and this number over here. So this will be negative 1, and then this will be positive 2. Then I'm going to plot these ordered pairs. I'll do that in blue. So I'll start with my vertex 0, negative 2. Then I'll go to 1, negative 1. Then I'll go to 2, comma 2. Then I will go to, on the other side, negative 1, comma negative 1. And then I'll go to negative 2, comma 2. And the 7's not going to fit. So I'm going to draw my smooth curve here. I'm going to sketch it best I can. So something like that. All right, now I'm going to graph f of x squared. So I'm going to make another row on my table. I put y here, and I should have put g of x since I'm dealing with multiple functions, but I'll put f of x here. Okay, and then this is just going to be 0, 0, and then 1 and 1, and then 4 and 4, and then this would be 9, but that's not going to fit either. I'm going to graph this in pink. So I'll plot my vertex 0, 0, and then I have 1, 1, 2, comma 4, and then over here, negative 1, comma 1, and then negative 2, comma 4. Then I'll draw my smooth curve through here. So now I have to compare my g of x graph to this f of x graph, and I can see that all I'm doing is just translating my original f of x graph down 2 units to get to my g of x graph. Every single point on my blue graph is just 2 units down from every single point on my pink graph. You can see 2 units, 2 units, 2 units, 2 units. So the transformation is a vertical translation of f of x 2 units down. Anyway, we've graphed both of our functions and we've described the transformations, so now we're done. For this example, we're going to graph g of x equals 4x squared plus 1, and then we're going to compare it to the graph of f of x equals x squared. So I'm going to make my table of values. So I have x, and I'll write g of x correctly this time. And I'm going to have my 5 things, and I'm going to put my vertex here. Okay. So for g of x, well, there's no b term, so I know my vertex is going to be, or the x value, I should say, is going to be 0, and then my y value is going to be this 1, because if I plug 0 in, this whole term drops out, and then my output is going to be 1, so it's going to be 0, 1, and then I'm going to surround my points. So I'll do 1 and 2, and then -1 and -2. Okay, and now I'm going to plug my values in. Okay, well, 1 squared is 1, and then times 4 is 4, plus 1 is 5. And remember, since my axis of symmetry is going to be where my vertex is, if this is 5, since this is the same distance away as these two numbers, this is also going to be 5. Now I'm going to do 2. 2 squared is 4. 4 times 4 is 16, and then 16 plus 1 is 17. So this will be 17, and this will be 17. So now I'm going to graph this. I'm going to use blue. So I have 0, 1, which is my vertex. Then I have 1, 5, which is right here. Then I have 2, 17, which is right about there. Then I'm going to do the symmetrical points right here and then right here. Okay, now I'm going to sketch my curve. Not perfect, but good enough. Anyway, now I'm going to graph f of x equals x squared. So I'm going to make another row in my table. So f of x. So now this is just x squared, so I know that 0 squared is 0, 1 squared and -1 squared is both +1. And then I get 4 here. And I'm sure I can fit some more points. So if I have a 3, that's going to be 9. And then if I have a 4, that'll be 16. So I'll plot these in pink, and then I can use my axis of symmetry to plot these points on the other side as well. So I'll use pink. I have 0, 0, 1, 1, 2, 4, 3, 9, and 4, 16. That's all that's going to fit there. And now I can just plot these points on the other side of my axis of symmetry, which in this case is going to be the y-axis. So that's going to be right here, and then right here, right there, and right there. Okay, now I'm going to sketch my curve. All right, so I've graphed my function successfully. Now I'm going to compare them. So if you look at the equation for the function, the 4 being multiplied by the x squared, well, that's going to be a vertical stretch by a factor of 4 units. So basically, every single point from the pink graph would be just multiplied by 4, the output, for the same input. And then the +1 means I'm going to then take that and translate it 1 unit up. Okay, so our transformations here is going to be a vertical stretch. I'm going to write this down. Vertical stretch, and with a scale factor of 4 units, and then a translation 1 unit up. Okay, and once again, you can tell that without even graphing, just by looking at the equation. This 4 means that we're going to have a vertical stretch, and then the 1 means I'm going to have a vertical translation 1 unit up. Anyway, I've graphed these functions successfully and then compared them, and now we're done. All right, so for example 3, we're going to let f of x equal -0.5 x squared plus 2 and g of x equal f of x minus 7. So first we're going to describe the transformation from the graph of f to the graph of g. Then we're going to graph f and g in the same plane. Well, right away, before I even graph it, I see that all I'm doing for my g of x is just taking my original f of x and then subtracting 7. So all I need to say for part A is that g is just going to be a vertical translation of f 7 units down because of this minus 7. This minus 7 is happening outside of my function. So anytime we have something that's happening outside of the function, it's going to be a vertical change. And then the minus 7 means I'm going to translate it 7 units down. So g of x is a vertical translation 7 units down from f of x. Okay, so now we're going to graph these two functions. So first I'm going to graph f of x, and I'm going to make my table of values. Okay, my vertex is going to be the ordered pair 0, 2. So I have 0 and 2. I see on my graph that I'm counting by 2's, so I'm going to count by 2's in my table as well. 2, 4, -2, -4. You could have counted by 1's, that would have been fine, but I think 2's will be better in this case. Anyway, if I plug in 2, I get 2 squared, which is 4, times negative 0.5, which is going to be -2, plus 2, that's going to be 0. Then I get a 0 here. And then over here, I get 4. 4 squared is 16. 16 times negative 0.5 is -8. -8 plus 2 is -6. And I'm going to see if I can fit one more on here. If I do 6. 6 squared is 36. 36 times negative 0.5 is -18, plus 2 is -16. So that will fit here. That'll go right here. So I'm going to put that down. And then that will fit over here on the other side of my table. So I'm going to graph this. I'll graph this one in blue. So I have 0, 2 as my vertex. Then I have 2, 0. Then I have 4, -6, and 6, -16. And then over here, I'll just plot the symmetrical points from my axis of symmetry, which in this case is the y-axis. Now I'll sketch my curve. All right, so there's my sketch of f of x. Now, if you notice, all I'm doing for g of x is just subtracting 7 from f of x. So what I can do on my table is just make my g of x. And instead of just plugging everything in to g of x, then subtracting 7, I can just take all of these outputs for f of x and then subtract 7 from those. So that's what I'm going to do. So -6 minus 7 is going to be -13. Then I get -7. -5, -7, -13, -23. Okay, now this is not going to fit on our graph, so I'll plot all these points. I'll do that in pink. So my new vertex is going to be the point 0, -5. So that'll be right here. Then I have 2, -7, so it'll be right here. And then I have the ordered pair 4, -13, which is right here. And then I'll draw these symmetrical points based on my axis of symmetry. I'll sketch my curve. So we can tell that I do have my vertical translation of 7 units down. So this point is 7 units down from this point 7 units down from this point, and so on with all these points. Now for part B, we're going to write an equation that represents g in terms of x. So if I scroll back up here, I see that g of x is just equal to f of x minus 7. So what I can do is just take my f of x value, what f of x is equal to, and plug it in to my f of x over here. This is just like substitution. And then I can just write over here, I'm going to do this on the side, g of x equals this f of x value, which is -0.5 x squared plus 2. I'm going to write that in parentheses. And then all minus 7. I'm going to scroll over to give ourselves some more room. So now, if I simplify this, g of x equals, well, I'll just write it without the parentheses first, 0.5, -0.5 x squared, I should say, plus 2 minus 7. And then all I got to do is combine my positive 2 and -7, and I get -0.5 x squared minus 5. and this is my new graph. Okay, and if we look over here, my vertex is 0, -5, which is consistent with what we've been doing. Anyway, I've successfully graphed both functions, compared them, and then rewrote an equation for g in terms of x, and now we're done. Solving real-life problems. A 0 of a function, f, is an x value for which f of x equals 0. A 0 of a function is an x-intercept of the graph of the function. For example 4, the function f of t equals -16t squared plus s sub 0 represents the approximate height in feet of a falling object t seconds after it's dropped from an initial height s sub 0 in feet. An egg is dropped from a height of 64 feet. Part A. After how many seconds does the egg hit the ground? B. Suppose the initial height is adjusted by k feet. How will this affect part A? So we're going to start with part A here. And we know that the egg is dropped from an initial height of 64 feet, which is our s sub 0. So I can take this 64 and plug it into s sub 0. All right, so I'm going to rewrite this function as f of t equals -16t squared and then plus 64, because that's my initial height that I'm dropping it from. And if we look at f of t right here, f of t represents the approximate height. And when the egg hits the ground, the height of the egg is going to be 0 because height is measured relative to the ground. So I can rewrite this as 0 equals -16t squared plus 64. All right, I'm going to zoom in here. Now, in the last chapter, we learned how to solve an equation like this by factoring, but now we're going to solve it by using square roots. So I'm going to subtract by 64 on both sides. So I get -64 equals -16t squared. Now I can divide by -16 on both sides. So I get 4 equals t squared. And now I'm going to take the positive and negative square root of both sides. But you actually only need to take the positive square root here, because if I take the negative square root of 4, that's going to give me a negative time, which would technically be going back in time, which isn't really realistic. So I'm just going to take the positive square root of both sides here. And I get t equals 2, and that's seconds. So we know that for part A, our answer is 2 seconds. It takes 2 seconds for the egg to hit the ground. Now we're going to do part B. Well, part B asks, if I zoom in here, suppose the initial height is adjusted by k feet. How will this affect part A? Well, all I have to do is add k to our initial height. So that's the adjustment. So I'm going to rewrite this for part B as f of t equals, I'm going to move over, -16t squared plus 64 plus k. Now, it doesn't tell us which direction that we're adjusting it, so I'm going to do plus k, and this could either be positive or negative. If I go up, it would be positive. If I go down, it would be negative. Anyway, now I'm going to do the exact same thing I did in part A and set this equal to 0, because that's when it's going to hit the ground. So I have 0 equals -16t squared plus 64 plus k. And then I'm going to move both of these terms to the other side to isolate my t squared. So I'm going to subtract 64 minus k minus 64 minus k. So I get -64 minus k equals -16t squared. Now I want to do the same thing, divide by -16 on both sides. Now I'm going to simplify this fraction. I'm going to break it up. So I have -64 over -16, which is 4. And then -k over -16, which is just plus k over 16. This equals t squared. And I'm going to take the positive square root of both sides, because once again, the negative square root is not going to make sense here. So I'll square root this and this. So when I get my solution, I get t equals, I'm just going to leave it like this, the square root of 4 plus k over 16. Now, if we look at what this means, if I look back in part A when I didn't have this k adjustment, I was just taking the square root of 4, and that got me 2 seconds. Well, if k is positive, if I increase k by a certain amount, that means the time that it takes for the egg to hit the ground is going to increase as well. If k is negative, that means that the time is going to decrease, because if this is negative, then 4 is going to get smaller. I'll be taking the square root of something less than 4, and if k is larger, I'd be taking the square root of something larger than 4. So if k is greater than 0, then t will be greater than 2. If k is less than 0, or negative, then t will be less than 2. Anyway, we've successfully finished this problem, and now we're done.